Good morning, everyone. Welcome to this talk on from monoliths to microservices to serverless and beyond. My name is Hugh Mckee. I'm a developer advocate at Lightbend, the company behind the Scala programming language. Many of you may be familiar with that. Akka, the actor model on the JVM, and so on. But here today, this is kind of a pictorial talk about kind of a broad landscape from monolith to microservices. So in this talk, I'm going to be kind of walking through this visual representation, I like to think in pictures versus words. So this is kind of an attempt to represent that. So in this diagram, as you can kind of guess, what I'm showing is that the big box on the left, this big green box on the left, is representing a monolith. And then next to that are a bunch of smaller boxes that represent microservices, like a microservice system. And then beyond that is a bunch of even smaller boxes that represent a serverless environment. So, and then finally at the end of the talk, I did this talk once before, and I'll say it again, I'm going to make a fool of myself because I'm going to try and predict the future, which it's just insane, but I like to think about the future, and I'm going to make a few predictions, and in the future you can laugh at me because of how wrong my predictions were, but things are moving so fast, we kind of have to at least start to project ourselves out into the future a little bit to try and anticipate where things are going and what that means for us individually in the jobs that we have. So going back to this picture, one thing that should become fairly obvious, and there was another talk yesterday that had a similar picture like this, is that we're moving from coarse-grained to ever finer-grained units of deployment, units of how we build our systems. And one question to ask is, well, why are we doing this? Well, there's a lot of different reasons, but I think the biggest one is that this should be the driving force. I mean, even though these newer things like serverless and microservices and so on compared to monoliths, we think of them as the cool technologies, they're things that we want to have as part of our skill sets. But ultimately, at the end of the day, the real driving factor should be here that you're doing these things to improve the velocity of innovation. The ability for us to actually add value to our systems that are useful to our customers, and to our business, and to the people that are paying us to build these systems. So if we're not doing these things to ultimately achieve this goal, then maybe you need to re-question why. And this is important, I think, because many cases people are saying, oh yeah, I want to get rid of that monolith because we're going to do some cool microservices. But they're thinking about the cool technology, but they're not necessarily thinking about, is this really going to improve our ability to innovate, to add more features to our systems more quickly? Now, some of the characteristics of this is that each of these, finer grain units, one of the objectives is that they're independently deployable. And more importantly, though, they're loosely coupled. And I was delighted to hear some of the talks yesterday that was really kind of hammering on this theme of when you're building these finer grain systems, an important characteristic should be that they are loosely coupled. I really think that this is very important for a lot of different reasons. We'll go into some of them as we go through this talk. So starting with the monolith, anybody recognize this shape and why I might have decided to use it as a monolith? I'll give you a hint. If you look at it this way, anybody recognize it? 2001, a movie that's 50 years old that back in 1968 tried to predict the future as what it would be in 2001. It was way off. I think they should have called it 2031. Maybe some of the things that they showed in that movie might actually come to fruition in maybe 2031. It's a fantastic movie. It was a groundbreaking movie, but one of the cool things was there was artificial intelligence, and very advanced artificial intelligence that the assumption was that would be available in 2001. The level of artificial intelligence that they showed in this movie, and they did it quite well, isn't quite here yet. and other things like the computer systems. Even back then, the way they were showing computer systems, lots of visualizations and so on. I think we're still slowly getting to that point. But in any case, every time I think of a monolith, I love this movie. I saw it, I've seen it probably 50 times and over the years. And every time I think of a monolith, I think of this shape. So in any case, it's 2001. So the monolith. Now, often there's a growing number of people that justifiably are saying, you need to really think about whether or not you should break down an existing monolith. And one of the rationale that they use I think is quite interesting, is they'll say, what makes you think you can build a microservice system if you can't properly modularize your monolith? And it's a really good question, but I think part of the counter to that is that, did we have sufficient tools that allowed us to compartmentalize our modules within a monolith so that it's like a visible surface to the module that other modules can see, but then there's also a private inside. And I think for the most part, for example, in Java, up until recently with the introduction of modules, the ability for us to do that at the implementation level really wasn't there. And in fact, in many cases, when developers create monoliths using Java, it's like everything's public. Almost everything's public. Public is just the default. And as a result, when you're trying to, say, decide if you're going to make a change to the monolith, what's the ramifications of that, it can be difficult because you don't know it's difficult to figure out who else or what other parts of the system are maybe interacting with the parts you're considering to change. But in any case, there's this idea of a monolith that's composed of modules. Now, another thing to consider is that like your landscape of systems across the company. And before I came to Lightbend, I worked at Hewlett-Packard, and through the whole 2000s, I was in enterprise IT. And at one point, there was this effort for us to reduce our data centers down from something like 85 down to 6 worldwide. And part of this effort was to catalog all of our applications and identify the applications that were worthy of being migrated into this new data center. And the catalog started out around 2000, and there was this huge effort to get the number of applications down to around 1,000. Well, this is what I'm showing here is 1,000 monoliths. Now consider decomposing all those monoliths into even finer grained deployable units that have to be managed and so on. You're talking about in the scope, the broad scope of it, like the entire enterprise. That's a lot of granularity. So maybe in some cases, if the innovation velocity isn't going to be significantly improved by going to some new technology, perhaps some monoliths should remain monoliths. Leave them alone. Focus on the ones where you get the most benefit. But moving on with microservices, the idea is one way that we've looked at it is that you take a monolith and you kind of look at it from the modular standpoint. I'm kind of blowing it up here, and then decomposing it down into microservices. So one approach that you hear about, I'm not sure how often it's used, is that you gradually replace functionality in the monolith with new microservices. And ultimately, the goal is to slowly, over time, replace the monolith. That's kind of a nice approach because in many cases, there's a big learning curve going from, say, building monolithic systems to building microservice systems. And in fact, in many cases, you see that you see different groups go through evolutionary waves where they implement microservices using their first style. They settle in on that. They understand what they've done. They start to learn about and appreciate some of the new ways that they can do it, and then they kind of go through the next evolutionary cycle. So this gradual, introduction of microservices into a system might give you that opportunity to learn, kind of go through your first evolutionary stage with microservices, and then iterate. All right, now there's a new pattern for the way we can do microservices, and I'll show you some of those in a bit. Continue on, though, taking, say, a microservice and breaking that apart. And the numbers, the ratios here are meaningless in what I'm showing. It was just convenient to take a square and break it up into 8 squares, in visually here. But the idea is that, in general, a function is a little bit more fine-grained than, say, a microservice. And I'll explain that in a little bit as well, kind of maybe a general idea. But then we get into serverless, and serverless is really, really interesting, I think. And thanks to, I think things got started with Amazon's Lambdas. That's when things started to catch, really get the attention. And I understand, like at Amazon, they can't almost keep up with the demand. There's so much movement to serverless that it's just really moving very, very quickly. But it's also evolved into what's called like function as a service. And there's a lot of other companies now and a lot of other frameworks and so on that are appearing that the whole topology, the whole environment of how we do serverless is evolving very, very quickly at the moment. But one of the things that kind of drives me nuts when you hear talks about serverless, or you read maybe an article or something, you say, well, of course it's not serverless. It's like, yeah, we know. We know there's still servers there. But the big difference is that when you look at before serverless, one of the big things that we had to think about was how much capacity do we have to run our stuff, right? And that capacity had roughly 2 dimensions. How much CPU capacity or processing capacity we have on one axis, and how much memory capacity we have in another axis. So that's what I'm trying to show here. So you get a process running in this capacity, and the challenge is that how much capacity is being used at any moment in time is pretty dynamic, especially the CPU capacity. So it's jumping around. This is one system, and then it hits a spike. And this is the scary part. You have to have sufficient capacity to handle those spikes, right? So you try and size all the, it might be VMs or physical hardware. You're trying to size it so that you have sufficient capacity. I know that you can do some things with elastic VMs and so on, like with Amazon, but a lot of us don't have the luxury of doing that. I know I didn't for a long time at HP. But then, the process runs along after the spike, and it goes down, sidling along, not doing much. Maybe it bounces up a little bit. Maybe there's couple little minor spikes. But then the really interesting statistic that kind of emerges from this, and I know this is for a fact at Hewlett-Packard, HP made servers, okay? And at its peak, when I was there was like 350,000 employees, and we had, I think it was around roughly 50,000 servers for enterprise IT, something like that. It was tens of thousands of servers. The overall utilization of those servers was around 10%. And that drove our management nuts, because it's like we're paying for all this capacity and we're on average only using 10%, and they would constantly beat on us. It would trickle all the way down to the development teams and say, can't you make it use more, more of the capacity? And it's like, and we'd, start babbling some technology stuff, and their eyes would roll back in their head and they'd go away, and it just stayed that way. So it doesn't really change with going to virtual machines. Like if you really look at virtual machines from this perspective, it's just divvying up those 2 dimensions. Virtual machines run on physical machines, and you're just divvying up. Some virtual machines get so much memory, so much CPU, and you kind of run things in those virtual machines. So this is kind of like the cloud. And I've heard from people that work for some of the cloud companies that guess what? The processing capacity that you rent and pay for from the cloud vendors, on average, you're using about 10% of that, because it's the same problem. And along comes Kubernetes, which is really awesome. It's very, it's a great environment, but it's the same game, right? In Kubernetes, you basically are giving Kubernetes a cluster of nodes, cluster of physical machines or virtual machines. It really doesn't matter, because Kubernetes looks at these things in the same way. You describe each machine with how much CPU capacity it has, how much memory capacity it has. It sums all that up, and one of the orchestration things that Kubernetes does really well is it figures out where to run stuff. And the way it basically works is you run a pod, and you describe a pod basically using those 2 dimensions. Like how much you put in a request for this pod needs at least this much processing capacity and this much memory capacity. Kubernetes uses that to figure out where each pod can run in a cluster. So whenever a request is made to run a pod, Kubernetes' job is to figure out. So like what I'm showing here in, say, the 3 of the nodes is that first node on the left is fully utilized because there's 4 pods running there and it's consumed all of its CPU capacity. But we don't have to worry about that anymore to a certain extent because Kubernetes is orchestrating that. However, we're still dealing with those 2 dimensions of CPU and memory. And that's, the game is still the same in Kubernetes. We have to have sufficient capacity to run everything. This is the beauty of serverless. Serverless abstracts all this away. And this is the less part of serverless. There's less friction. In this kind of way, I'm actually starting to prefer the term frictionless versus serverless. And what I mean by friction is that, in a way, I'll kind of define my little definition of it. It's anything that distracts you from innovating business technology. And if we look at our jobs right now, there's a ton of stuff that distracts us from building business functionality. And serverless moves us way into the right side of that a way of doing things, where it's reducing a lot of the friction that was involved in doing it. Because in serverless, basically say, here's my function, run it please. And then the deal is you pay for how much CPU it uses, how much memory it uses, how many hits it gets, over the wire, those types of things. There's very relatively simple metrics. And then the serverless provider is assuming the responsibility of having sufficient capacity. But that's not our problem anymore. That friction is gone. And that I think is one of the best things about it. Now, if, like Kubernetes is providing serverless functionality, and if you're running Kubernetes on-premise, then there's somebody on-premise that's still worrying about capacity, but the game is still even there, it's changed. But I think the big advantage is going to be with the cloud, the cloud providers providing the serverless service, is that you don't worry about that anymore. We don't have to worry about, capacity. We just worry about like our bill, right? We worry about the efficiency of our functions. When you're running a function, you're getting your cost numbers back from it as it's running, say, in production. And when you make changes to it, maybe you're making optimization, or maybe you're adding a new, some new functionality to it, and you see that the change. Does it cost more? Does it cost less? You're getting that some really, I think, very, very powerful feedback. So moving back to monoliths, microservices, and so on again. Now, often when we think about breaking up monoliths, the focus is on breaking up the code. But there's also a database involved. And typically, a monolithic hunk of code has a monolithic database associated with it. And often a pattern is that when many start to do some form of microservice, they break apart the code, but breaking up the database is often much more difficult, especially if you work in an enterprise space. If you're working at a smaller company, maybe this isn't a problem. But I know like at HP, for example, we had data architects. We had DBAs. They owned the database. We made suggestions about what the database should look like, but they ultimately decided what they look like. And I was gone before this stuff came along, but I'm kind of imagining the kind of discussions people have in enterprises going back to their database people and saying, hey, we're supposed to be breaking up this database. No, you're not breaking up this database. We got 100 tables in here. It took us forever to design this thing, and you're not breaking it up. Forget it. But the problem is this is tight coupling. Tight coupling introduces friction. Friction slows you down. So for example, say you and I are working on a certain microservice, and we want to make some schema changes to the database. The friction starts because now we got to figure out who else will be impacted by this change. We got to talk to them. We got to negotiate with them. And we probably will have to do a coordinated deployment when the schema change goes into effect. Friction, 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 friction is slowing us down. So the idea is, and again, I was delighted to hear this yesterday over and over in a number of different talks, is that each microservice should own its own. Now, I heard own its own database, but I'm going to qualify it a little bit differently, where each microservice should own its own schema. Don't really care where the schema is running. I care about the structure of the schema and that my team has control over the structure of that schema, and I don't have to negotiate with anybody else. So then, this is a form of looser coupling. Not only is our code loosely coupled, but now our data, our schema is loosely coupled. Because the idea is that each microservice, you should think of it as a black box. And actually, you should do a context switch between, when you're talking about a microservice with your team, you're talking about the inside of the microservice. When you're talking about your microservice to somebody outside of your team, you're talking about the outside of the microservice. Beyond the barrier of the microservice. There was this excellent article written by a guy named Pat Helen, who's written a number of really good articles. Just do a search on Pat Helen, and he's written one. But this one in particular was something like data on the outside versus data on the inside. This is essentially what he was talking about in this article was that, or this blog post was that, what happens inside of microservice is private to the microservice. And this was actually in the service-oriented architecture days when he wrote this, but it still applies to microservices. But the contract of how the microservice looks on the outside is another thing. So again, there should be this context switch is like, you never talk about your schema to the outside world, for example. Because if you let it leak out, they're going to want to get to it, right? And then coupling starts, friction starts. You don't want to do that. So the idea is that microservices from code to data should be independent as possible. Now, moving along, rearranging, say, a microservice system into a ring, and to show something like this pattern, which is very common, where there's a service on the bottom that is referenced by, say, these other 4 services towards the top. And this is a really easy thing to implement with the tools that we have. Each of the top services is just doing RESTful, say, retrievals, RESTful whatever calls to this bottom service. So there's this coupling between these services. And guess what? If the bottom service gets unhappy, it goes down, or maybe even worse, it slows down. The blast area, the damage that's caused is beyond just the service itself. This is a form of, really, it's a remote procedure call. These other services are making remote procedure calls into the service on the bottom. And this is, in a way, perpetuating the monolith. In the monolith, everything called each other internally, and we're real used to it, and everything's cool. When we go to microservices, oh yeah, we can do this RESTful stuff, so we can basically do remote procedure calls. It's like, that's coupling, that's tying services together. And it might not slow down innovation so much, but you're taking the risk of it could really hurt you in production in terms of, again, the blast area that's caused by a critical service not behaving well. An alternative to this is what I'm trying to show here, and let's walk through a scenario here where we got a microservice system, same number of microservices, but now they're all either publishing or subscribing or both to different topics on a message bus. So kind of walking through a scenario here where some of these light blue services, just for fun, I'm saying that these are analytic services. And this isn't really for this audience, but it's more for other audiences where when we talk about like artificial intelligence and so on, it's, oh yeah, we're going to be doing this training and blah, blah, blah. They're all talking about all the things that they do with the services. Like, I don't care. All I care about is that that's what's happening on the inside of that service. What's happening on the outside of that service is that it's consuming data and it's producing data. That's all I care about on the outside. On the inside, it's doing all this cool machine learning, whatever, but that's an internal detail. So in any case, say this one service, hopefully you can see the red arrow pointing it's towards the right, pointing down to this one service, and I put a little band around it. This service, and I'm not showing it, what's stimulating it, but something's happening, and this service is making the decision to publish something. So it publishes a message to a topic. It doesn't care who consumes it. That's not its responsibility. It just simply publishes the message, and it's done. Now, there are subscribers to this message, say, and I'm showing that here. So there's, in this little scenario, there's 3 subscribers. So we're kind of going through this cycle. This one service is, something's happening, is publishing a message. These other services pick it up, and we're just happily going along. Things are happening asynchronously here, and we're just moving along. But now, this other service, which happened to be one of the ones that I showed as a smart service, say it's a fraud detection service. It was looking at these messages and going, hey, Hugh's account looks like something funny is going on. So I'm going to publish a message saying, hey, Hugh's account looks kind of stinky. Maybe I don't like it. So it just publishes that. It just so happens that there's other services that are interested in that. One of them being our little star service, the one that was generating all these messages. And now that service, it was made aware of the fact that maybe if more activity happens with my account, that maybe it should change its behavior. Maybe it shouldn't allow, say, my account to be used anymore. Maybe it should lock it down. Another scenario is that, say, one of the subscribers is currently offline. And let's walk through this scenario again. So the service on the on the left is publishing. 2 of the 3 subscribers are currently up. They're fine. They're just keeping up. And say 3 messages were published. That other service is currently offline. Nobody cares. And then all of a sudden, this service comes back online. So it catches up. This is another example of where loosely coupled services using asynchronous messaging, where you have the code is, I think, often very simple. It's simple. It's much simpler to publish than have to implement circuit breakers and retry logic and all these types of things that is often used in a more synchronous type of an approach. So I think this is a pattern that is kind of one of those things where it's like your first evolutionary step of your microservice might be synchronous remote procedure calls type of style, and then maybe your second or third evolution of your microservice system might start to move more towards something like this. So finally getting into serverless. Now serverless is really interesting, and there's different styles that are kind of emerging for the way what functions do. And a lot of times right now we're hearing, well, it's early days and the kinds of things that you can do are kind of limited, but that's not holding people back. I've seen JavaScript systems written using serverless, and man, they're just doing CRUD-based stuff, and it's like, Yahoo, okay, get out of my way, I'm going to build my system. And people are saying, yep, we completely took a old system and we completely re-implemented it in microservices, and nothing seems to be holding them back. Plus, things are evolving very, very quickly in terms of the kinds of things that the tools and technologies that are coming online for serverless. So this is one example, and I'm just calling it a synchronous function. This is a real common pattern where HTTP requests come in, the request comes into to a function, the function's stateless. Maybe it does some kind of CRUD-like retrieval of state, changes the state, and then persists the state back down to the database, and it's done. And it sends back a response. Pretty cool, right? We can do a lot of stuff with this kind of a pattern. Another pattern, though, is where you have functions that are participating in their subscribers on one topic. They're doing some work. They might be persisting something to some kind of a database. and maybe they're publishing something out. So this is a really interesting pattern, I think, and a little hybrid. And this is more me than I think for real. But I kind of envision, say, a synchronous function. So HTTP request comes in, do some work, response goes out. But maybe one of the other things that the function does is it also publishes something to a topic. But the idea is that I kind of like the term nicely constrained building blocks. With serverless, it's like we had guidelines and maybe some frameworks and so on for helping us to build microservice systems, but there weren't a lot of constraints. There weren't a lot of guide rails. And in fact, one of the frameworks that it's called Logom. It's an open source framework, and the idea of that framework was to put some guide rails onto the implementation of microservices. But in general, it was pretty wide open what we could do, and as a result, we did a lot of different things. If you look at everybody's different implementation of our microservice system, you probably find wide variability. In fact, I just saw a study recently where the majority of microservice systems do the HTTP REST remote procedure call kind of style thing. And a lot of the microservice systems use a monolithic database. Not that that's a bad thing, it's just that it could be better, right? Here, the building blocks are a little more constrained. And it's kind of like Lego blocks. Lego blocks, the little blocks where you can plug them together and build really interesting things. Lego blocks follow a very simple pattern, but people build marvelous structures with Lego blocks. And I think it's kind of the same thing here. Often I'm a big fan of the actor model. The reason I work at Lightbend is because of Akka. I fell in love with Akka when I was at HP, and I lucked out and ended up getting a job at Lightbend. And to me, these serverless functions feel a lot like actors. In fact, when you read articles about it, often you'll hear the term actor brought up. And there's some really interesting patterns that are already starting to emerge, and here's one of them. You have this function on the left that is doing something that results in, say, making a change into, an Amazon S3 or DynamoDB. Those databases are already enabled so that when changes are made to data in those databases, that can trigger publishing a message to a topic that other functions can pick up. So now you're starting to chain functions together through a series of events. And this really kind of, I think, naturally leads us into event-driven types of systems, which I kind of alluded to with the microservice pattern, with publishing and subscribing. That's an event-driven type of a system. Here, I think it's almost intuitive that we should, that we move in that direction. So as a result, there's already talk. I saw a really great Amazon presentation recently where they were kind of talking about this, that there's an event flow that's going on from function to function. And it's this publish subscribe. So the publisher doesn't care who the subscriber is. And the subscriber really doesn't care who the publisher is. So there's this nice decoupling that occurs. But at the same time, as we're assembling these kind of systems, it's kind of like plugging Lego blocks together, right? So we know, us as the architects and the implementers of these systems, that these things work together. But we have some of that loose coupling so that if we want to change one of these functions, maybe we're changing the inside of the function, but we're not changing the outside of the function, which is fine. When you start to change the outside of the function, you start to affect the outside world. But when you're changing the inside of a function, maybe making it more efficient or adding some new way of doing something or whatever it does, that's another thing. Another part of it is that, introducing more steps in the flow. Or, the last time I did this talk, somebody asked about forks, in a stream, where things kind of, one output goes to two inputs. Well, in this kind of a flow, I'm not showing it here, but that's a very natural thing. You have one producer, one publisher, multiple subscribers, which I showed previously. So I think the behavior and the style here is very, very interesting. And it's already getting very exciting, but it's going to get more exciting. And this goes into the crazy part. So this whole thing of stringing functions together, I think, is very, very powerful. And one of the things that is already starting to happen, but I think we need to start to think about it, is that I show the input and output on the left as red and green. So the input is red and the output is green. And that's kind of our normal cycle. We're so used to this input-output cycle. You know, a request comes in, the thing that got the request does some work and sends a response back. But it's like, when you think about it, it's like, wait a minute, we don't work that way. We hear something, we see something, we feel something, and we don't react with our ears or with our eyes or with our nerves. We react, and maybe we talk, or we scream, or we run, or we say something, right? So the input-output in a natural system isn't like this real tight request-response cycle. It's more of this where, the stimulus comes in at one part of the system, and the response comes out from another part of the system. So all the way on the right here, I'm showing maybe a response. And maybe there's multiple responses. And this, I think, is going to be very natural as well, because when you look at the edge of the system, the glass. I mean, one way to view a system is that it's surrounded by this big sphere of glass, which is the glass that we're all poking at on our phones, right? A system is surrounded by all this glass that we're poking at all the time. And the devices that we run, or on the browsers or whatever, however we're feeding input into a system, these are the edge of our system. Well, these edge systems, guess what? What's a click? What's typing a character? What's entering a field in a form? They're treated as events. These are stimulus coming into a system, and then these events are fed to the back end. The back end responds to it, and what I'm saying here is that maybe the output comes downstream. I think it's getting kind of more to a more natural flow, a flow that nature's used all along. But this is doable. We already have WebSockets, for example. And Amazon has already done this. I don't know if some of the other vendors have done this, but the idea is that the client can connect, to the system through a WebSocket, which means we have a two-way communication. It's all asynchronous. And the messages back to the client are coming from these functions, but it's kind of the publish-subscribe again. These functions are publishing, hey, I've got this message to send to this client. Now, how the message actually gets routed to the client, that's the less part. We don't care about that. The system handles that. So what we're caring about is that, yep, we got an input. We're carrying forward some processing of that, and then there's output going back to the client at various stages of the processing, downstream, different stages of the stream that we're processing here. Another one, though, is that very often, almost all the time you hear, yeah, the serverless functions are stateless. And that's fine. That's a very viable pattern, because not everything needs to be stateful for a long time. And what I mean by that is that even though we're saying that something's, you build a stateless system or you build a stateless serverless function, the situation is that there's still state you have to deal with. And in a stateless situation, you're lifting that state out of its persistence, out of the rust or out of the electrons or whatever. You're bringing it into memory. You're making changes to it, and you're persisting changes back. So it's all that lifting. Lift up, change, push back. And then you throw the state away. And that's fine, because if the state's not needed soon, again, then what's the point of having it sit around in memory, right? But there are patterns where doing that heavy lifting all the time does come at a cost. And going back to the ever-loving order scenario. You have an order, you have a customer, they're sitting there on their device, smashing the glass, and they're adding an item, removing an item, updating an item. All these things are events that are being sent into the system. The system is constantly changing the state of, guess what, an entity, a business object. So keeping that business object around where it's readily accessible without having to constantly lift it out of the database, change it, throw it back down in the database and throw the state away has a benefit, reduces cost. So this work is already happening. There's actually, when I started putting this talk together, I knew about what we're doing in my company. It's called Cloud State. About a week before I did this talk a few weeks ago, I heard about another one, I think it's called State Fund. Then last week, I heard about another one from Microsoft. It's called DAPR, DARPA, DARPA, whatever. But in any case, I think it's Distributed Application and Runtime or something. And they provide stateful serverless. So as I said earlier, the stateful part, the serverless technologies are advancing very, very quickly. And boy, they're really advancing very, very quickly. This, I think, is very exciting. We get a performance optimization, but at the same time, the friction is significantly reduced. Like with the implementation that we're doing for what we're calling stateful serverless, is that it's using the event log pattern, or the event log way of doing things, where when a function comes to life for a particular business object, it's rehydrated with its state from the database. It's replaying all the events. Now the function is in memory and it has its state. But that from that point on, every hit to it, every action that's being performed, add item, remove item, update item, the only I/O that thing is doing is it's emitting events that are going back in the event log. It's not constantly picking up the state, bringing it into memory, changing it, and pushing something back down. It's the state's in memory, in one place, in the cloud, for that, say, that order, instance of an order, and it's constantly getting updated, and we're just doing, the event logging type of thing. The coding for this, the coding is, there's a method or a function, that's being implemented in like Rust and Go and Python and JavaScript and Scala and Java and whatever. The pattern is that there's a method that rehydrates the object. There's a method that you call to persist new events, that type of thing. So we're not worried actually about the persistence part. We're just having to implement a few methods and call a few methods, and that's it. Frictionless, the whole frictionless thing. So getting back to it, it's starting to feel like we're moving in the right direction, finally, and we're moving towards a system that feels like the kinds of computing systems that nature has built over time. It's built of a large collection of very fine-grained processors. That's the way our brains work. That's the way sensory systems work in every living thing around, everything that can move. So we're kind of getting, into this whole, I'm thinking way ahead, and this is where I'm getting crazy, but it's like, it feels like we're moving towards in the right direction, a more biological direction. So that's it. The tour, the visual, this is like a comic book. It was all pictures for the most part. The three projects I talked about were, look up cloudstate.io or statefund.io or DAPR.io. Really, really interesting stuff. This talk is available at that link there, and I really appreciate your attention. Thank you very much.